Electrical metallic tubing, or IMT, cannot be used to feed motor starters and motors from a 4160-volt service. Acceptable conduit types are rigid metallic conduit, or RMC, and intermediate metal conduit, or IMC. In certain cases, Schedule 80 polyvinyl chloride, or PVC, conduit may be permitted for use in concealed locations within a mechanical room, subject to approval by the local electrical inspector. The conduit must have a minimum trade size of 1 inch for a 4160-volt service. The conduit must be securely supported and protected from physical damage. The conduit must be properly grounded and bonded. All wires and conductors must be properly rated for 4160 volts. The installation must comply with all applicable electrical codes and regulations. When dealing with high-voltage electrical systems such as 4160 volts, the selection of appropriate conduit is critical for safety and compliance with electrical codes. The primary function of conduit is to provide a protective pathway for electrical conductors, shielding them from physical damage, moisture, and other environmental factors. Different types of conduit are available, each with its own characteristics and suitability for specific applications. Firstly, let's discuss electrical metallic tubing, or IMT. EMT is a lightweight, unthreaded metallic conduit commonly used in commercial and residential buildings. It is relatively easy to install and is suitable for many applications where physical protection requirements are moderate. However, EMT is generally not approved for high-voltage applications such as feeding motors and motor starters from a 4160-volt service. The reason for this restriction is that EMT may not provide sufficient mechanical strength and protection for high-voltage conductors. High-voltage systems can generate significant electromagnetic forces during fault conditions, and EMT may not be able to withstand these forces adequately. Additionally, the thin walls of EMT may be susceptible to damage from physical impacts or corrosion, which could compromise the insulation of the conductors and create a safety hazard. Secondly, we have rigid metallic conduit, or RMC. RMC is a heavy-walled, threaded metallic conduit that provides excellent mechanical protection and is suitable for use in harsh environments. It is typically made of steel or aluminum and is available in various sizes and coatings to resist corrosion. RMC is approved for use in high-voltage applications and is often the preferred choice for feeding motors and motor starters from a 4160-volt service. The thick walls of RMC provide superior protection against physical damage and electromagnetic forces, ensuring the integrity of the conductors and minimizing the risk of electrical faults. Thirdly, consider intermediate metal conduit, or IMC. IMC is a lighter-weight version of RMC that offers a good balance of strength and cost. It is also a threaded metallic conduit and is approved for use in high-voltage applications. IMC provides similar protection to RMC but is easier to handle and install due to its lighter weight. It is often used in applications where RMC is not required but EMT is not sufficient. Next, we have Schedule 80 polyvinyl chloride, or PVC conduit. Schedule 80 PVC conduit is a non-metallic conduit that is made of rigid polyvinyl chloride, or PVC plastic. It is corrosion resistant and is suitable for use in wet or corrosive environments. While PVC conduit is generally not approved for use in high-voltage applications in all locations, it may be permitted in certain cases for concealed locations within a mechanical room subject to approval by the local electrical inspector. The use of PVC conduit in high-voltage applications is typically restricted due to its low mechanical strength and temperature resistance compared to metallic conduits. However, in certain controlled environments where the risk of physical damage and high temperatures is minimal, PVC conduit may be acceptable. Now let's talk about minimum trade size. Regardless of the type of conduit used, it must have a minimum trade size of 1 inch for a 4160-volt service. This requirement is specified in electrical codes to ensure that the conduit has sufficient internal space to accommodate the conductors and provide adequate ventilation to prevent overheating. The trade size of conduit refers to its nominal inside diameter and is typically expressed in inches. It is important to select the correct trade size of conduit to ensure that the conductors can be easily installed and that the conduit can effectively dissipate heat. Proper support is very important. The conduit must be securely supported and protected from physical damage. This requirement is critical to ensure the long-term reliability and safety of the electrical system. Conduit support should be installed at regular intervals to prevent sagging or displacement of the conduit. The spacing between supports will depend on the type and size of conduit, as well as the specific requirements of the electrical code. In areas where the conduit is exposed to physical damage, additional protection may be required, such as installing a guard or barrier to prevent impact. Grounding and bonding are essential. The conduit must be properly grounded and bonded to ensure that it is at the same electrical potential as the surrounding equipment and structures. Grounding and bonding help to minimize the risk of electric shock and prevent the buildup of static electricity. Grounding is typically achieved by connecting the conduit to a grounding electrode system, such as a ground rod or a metallic water pipe. Bonding involves connecting all metallic parts of the electrical system together to create a low impedance path for fault currents. Conductors must be rated properly. All wires and conductors must be properly rated for 4160 volts. This requirement is fundamental to ensuring the safe and reliable operation of the electrical system. Conductors must be selected based on their voltage rating, ampacity, and insulation type. The voltage rating of a conductor indicates the maximum voltage that it can safely withstand. The ampacity of a conductor indicates the maximum current that it can carry without overheating. The insulation type of a conductor determines its resistance to moisture, chemicals, and other environmental factors. Compliance is paramount. The insulation must comply with all applicable electrical codes and regulations, including the New York City Electrical Code. Electrical codes and regulations are established to ensure the safety of electrical installations and to protect people and property from electrical hazards. These codes and regulations specify the requirements for the design, installation, and maintenance of electrical systems. It is essential to consult with a licensed electrician or the local electrical inspector to ensure that the installation complies with all applicable codes and regulations. Here are some additional considerations for high-voltage conduit installations. Firstly, consider the environment. The environment in which the conduit is installed can have a significant impact on its performance and longevity. In corrosive environments such as those containing salt water or chemicals, it is important to select conduit materials that are resistant to corrosion. In high-temperature environments, it is important to select conduit materials that can withstand high temperatures without degrading. Secondly, consider the accessibility. The accessibility of the conduit can affect the ease of installation and maintenance. In areas where the conduit is difficult to access, it may be necessary to use specialized tools and techniques to install and maintain it. Thirdly, consider the cost. The cost of conduit can vary depending on the type of material, size, and quantity. It is important to consider the cost of conduit when making material selections, but it should not be the only factor. The safety and reliability of the electrical system should always be the top priority. Now let's delve deeper into the specifics of selecting and installing conduit for 4160 volt motor and starter circuits. The primary consideration, as emphasized, is the prohibition of electrical metallic tubing, or EMT, for such high voltage applications. EMT thin wall construction simply doesn't offer the robust physical protection and fault current withstand capabilities demanded by high voltage systems. This is especially crucial in an environment like a mechanical room, where potential for physical damage from tools, equipment movement, and other activities is elevated. When choosing between rigid metallic conduit, or RMC, and intermediate metal conduit, or IMC, several factors come into play. RMC offers the highest level of physical protection. Its thick walls provide exceptional resistance to impact, crushing, and corrosion. This makes it ideal for environments where the conduit is exposed to significant physical stress or harsh conditions. However, RMC is also the heaviest and most expensive option. IMC presents a compromise. It's lighter and less costly than RMC, while still providing adequate protection for most high-voltage applications. IMC thinner walls make it easier to bend and install, which can save time and labor costs. The decision between RMC and IMC often hinges on a cost-benefit analysis, weighing the level of protection required against the budget constraints. Polyvinyl chloride, or PVC, conduit, particularly Schedule 80, is an interesting case. While generally not favored for high-voltage systems due to its lower mechanical strength and temperature limitations compared to metallic options, it can be considered for specific concealed locations within a mechanical room, subject to the approval of the local electrical inspector. The key here is concealed. If the conduit run is buried within walls or otherwise protected from physical damage and direct sunlight which can degrade PVC over time, the risk is mitigated. Furthermore, the approval of the local electrical inspector is paramount. They will assess the specific installation conditions and determine whether PVC is an acceptable alternative. Factors they will consider include the ambient temperature, the presence of corrosive substances, and the potential for mechanical stress. Regardless of the conduit type selected, the minimum trade size of 1 inch for a 4160 volt service is non-negotiable. This requirement stems from the need to provide adequate space for the conductors, facilitate heat dissipation, and ensure ease of installation. Using a smaller conduit size can lead to overheating, insulation damage, and increased risk of electrical faults. Proper support and securement of the conduit are crucial for maintaining its integrity and preventing damage. Conduit support should be installed at intervals recommended by the manufacturer and in accordance with the New York City Electrical Code. These supports should be designed to withstand the weight of the conduit and conductors, as well as any potential mechanical stresses. In areas where the conduit is exposed to vibration or movement, vibration isolators or flexible conduit connectors may be necessary. Grounding and bonding are essential safety measures for high-voltage conduit systems. The conduit must be effectively grounded to provide a low impedance path for fault currents, minimizing the risk of electric shock and equipment damage. Grounding is typically achieved by connecting the conduit to the building's grounding electrode system using grounding bushings and conductors of appropriate size. Bonding involves connecting all metallic parts of the conduit system together to ensure that they are at the same electrical potential. This prevents the buildup of static electricity and reduces the risk of arcing. The selection of wires and conductors for a 4160 volt system is critical. These conductors must be specifically rated for 4160 volts and must have insulation suitable for the operating temperature and environmental conditions. Common insulation types for high-voltage conductors include cross-linked polyethylene, or XLP, and ethylene propylene rubber, or EPR. The ampacity of the conductors must be carefully calculated to ensure that they can carry the full load current of the motor or starter without overheating. This calculation must take into account the ambient temperature, the number of conductors in the conduit, and any directing factors specified in the New York City Electrical Code. Finally, adherence to all applicable electrical codes and regulations, including the New York City Electrical Code, is non-negotiable. The Electrical Code provides detailed requirements for the design, installation, and inspection of electrical systems, including high-voltage conduit systems. It is essential to consult with a licensed electrician or the local electrical inspector to ensure that the installation complies with all applicable codes and regulations. This will not only ensure the safety of the installation, but also prevent costly rework and potential legal liabilities. In summary, installing conduit for 4160 volt motor and starter circuits requires careful consideration of several factors, including the type of conduit, the minimum trade size, proper support and securement, grounding and bonding, conductor selection, and compliance with electrical codes. Ignoring these factors can lead to dangerous and costly consequences.